Hello, everyone. Good morning, good afternoon, or good evening. The authors, distinguished session chair, and invited guests. Welcome to Technical Session 12E. I'm Sanskriti Khankar, and I will be moderating this session today. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it's my great pleasure to welcome you to the 11th International Conference on Information and Communications Technology for Sustainable Development. That is ICT4SD 2026 in Goa, India. The 11th edition of the conference is being conducted in a hybrid mode. The physical conference was held on 9th July in Goa, India, while the virtual conference is being conducted via Zoom from 9th to 11th July 2026. I hope you enjoyed today's informative and engaging technical presentations. In this session, we have 10 paper presentations. Each presenter will be allotted 10 minutes for the presentation, followed by 2 minutes for Q&A. At the 9-minute mark, I will give a gentle reminder so that we can maintain the schedule. I also request all participants to stay connected with us until the closing remarks. If you have any questions or require any assistance during this session, please feel free to send in the chat box. Now I'd like to introduce the session chair for this session. Dr. Lovesh Kautik Ahire is an assistant professor in the Department of Information Technology at Vishwakarma Institute of Technology in Pune, India, specializing in machine learning, quantum computing, and generative AI. With over 17 years of combined experience in academia and industry, he actively contributes to teaching, research, and the application of emerging technologies in information technology education. Welcome, sir. Now let's begin the presentations. Our first author is Rajashri Sahaji Katkar, who will be presenting their paper titled A Lightweight and Interpretable Deep Learning Review Framework for Real-Time Grape Leaf Disease Detection. Rajashri, you may start your presentation.
Hello, good afternoon. Am I audible?
Good afternoon, Rajashri. Yes, you're audible.
My screen is visible.
Yes.
Good afternoon, everyone. Myself, Rajesh Katkar. I'm research scholar in Department of Computer Science and Engineering at Sanjeevani University, Kopargaon, India. My co-author is Dr. Ajay Sinkar Singh, who is also same department. Today, I'm pleased to present our research title, a lightweight, interpretable deep learning review framework for the real-time grape leaf disease detection. This paper ID is 17880, and this paper is being presented at International ICT4SD conference. Thank you for giving me this opportunity to present our works. Let's begin. These slides here is quick look at what we'll cover in that presentation. Actually, there is 8 parts. First is the introduction and motivation, where why this problem is matter. The second is the literature review, what other researchers have done. The next is the research gap, what is still missing in that proposed research work. Next is the proposed research framework. Next, system architecture, key formulas which are used in current research, expected result, conclusion, and references. Let's start with the first part. Here, the actual problem, the grapes are important crop. They are used for the eating fish and making a juice, raisin, and wines. But the grape can get sick due to the 5 different diseases, most damage. The first is the black root, downy mild, powdered mild, leaf blight, and black disease. These diseases attack the leaves. This lowers the quality and amount of fruit, causes big financial loss for the rural area and different farmers. Today, the most farmer checks their plant by the human eyes. This is a slow and mistake are easy to make, especially in a early stage of the diseases. Deep learning can detect these diseases from photos very well, but most of these models are heavy. They need powerful computers and cannot run on a phone or any drone in a real field. Here, the literature survey, there are different approaches we have to use. Let us look at what other researchers have tried. The first approach is the traditional machine learning. The older methods use handpicked features like a color and shape with the classifiers like a SVM and KNN. The best result here was about 96.66% accuracy with the KNN. The second approach is the hyperspectral images. The hyperspectral images, this use the spatial cameras that see beyond normal light. It can find disease early, but the cameras are expensive and hard to use on a real field farm. The third is the deep learning model that like ResNet 50, VGGNet 16. These reach very high accuracy, near 99%, 99.67 percentage, but need strong computers. The next approach that is lightweight models like MobileNet V3 and EfficientNet. These also reach over a 99% accuracy, but run much faster and need less computation power. The fifth approach is the transformer model, and these are newer and powerful, reaches about 98.6% accuracy. The sixth is the explainable AI tools is used like a GradCam. These uses see which part of the leap is model is looking at. It reaches up to 99.91% accuracy in some studies. The next, the research current research gap, the existing studies that the first gap is research gap is the most paper only care about the accuracy. They do not think about speed or model size, which is matter a lot of phones in a field. Second research gap, second gap is very few papers compare lightweight models directly against heavy models for the real time use. Next gap is the third, that is not many studies combine lightweight model with explainable AI like a GradCam together. The next gap is the most models are trained on a clean lab quality photos, not on a real field farming photos. Like a fifth, the few papers gives a full ready to use system for the phone, drone and edge devices. And the last six, our focus is this paper bridge the gap between lightweight plus interpretable plus real-time deployment for the practical agriculture use. This is our focus. Next, proposed framework. Now, let me explain our framework that is five simple stages. The first is the pre-processing. We take photo of a grape leaf, resize it, clean it, and we can create extra training image by rotating, clipping, and zooming the original photos. Second stage is the use MobileNet V3 pulls out of the important features from the images and it fast and need very little computation power. The third stage is the CBAM use, that is convolutional block attention model is used. This attention model tells us the model which part of the image matter most and both features which location on a leaf. The next fourth stage that is SVM classifier use. This classifier uses the features to decide which disease is present on a grape leaf. Last five stages, we use explainable AI, that is GradCam, create a heat map. This shows in a color exactly which part of the leaf looks disease. This helps farmer trust and understand the result also. The next key technical components in that proposed research work, that is this slide shows the math behind the framework. That is the first, MobileNet V3 split one big calculation into the two small ones. This is called depth-wise separable convolution. This cuts the computing work by about 8 to 9 times without losing much accuracy. The second, that is CBAM, that is convolutional block attention model. That this attention model has the two parts. First is the channel part, and second is the spatial attention block. The channel attention finds which features are useful, and spatial attention finds the which part of the image is useful. Together, they sharpen the model focus on a disease area. The third is the GradCam checks how much each feature affects in final answer and turn this into the color heat map on the leaf images. And last, SVM classification is used, is draw the boundary between the different disease classes using the features from MobileNet V3 and CBAM. We pick the class with the highest score. The main point, every part of our design is the choose to keep the model small, fast, and easy to understand. The comparison part, that is a lightweighted model versus heavy models. This table shows the Heavy models like VGG16, ResNet 15, DenseNet 121, Swing Transformer use very high accuracy, but they are slow, need a lot of parameter, and cannot run on a phone or small devices. The lightweight model like MobileNet V3, EfficientNet, ShuffleNet are the fast, small, can run on edge devices which only small drop in accuracy. So the MobileNet V3 and EfficientNet give the best balance, high accuracy, small size, fast speed, and they work well on edge devices. This is why we choose the MobileNet V3 in our backbone. Expected result, that is based on our design and similar studies, we can expected strong result. We expected accuracy above 99%, precision above 98%, recall again 98%, and F1 score is also greater than 98%. Looking at the table, the other methods like inception resonate V2 reach very high accuracy but cannot run on edge devices. MobileNet V3 with a GradCam alone reaches 99.66% and does not. It also run on edge devices. The our framework built on this.
Excuse
We
me,
add.
Rajashri. Sorry to interrupt you. This is just a gentle reminder that 1 minute is left for your presentation.
Okay, okay, okay. Our framework built on the in our framework we can add CBAM attention and SVM classification. We expect this is to give over a 99% accuracy while keeping model high and edge device friendly. So conclusion and future scope, that is we review many methods for grape leaf disease detection, traditional machine learning, deep learning, lightweight models, transformer, and explainable AI. We found that the deep learning works better than the older method, but most deep learning models are too heavy that not useful in a real farming. So we propose new framework, MobileNet V3 for the fast feature extraction, CBAM for the attention, SVM for classification, and GradCam for to explain the result. We expected over a 99% accuracy with a small, fast model. For future work, we plan to test on real farming, and add sensor data for the temperature and humidity. Use federation learning across many farms to protect the data privacy, and build a mobile app so farmer can use this directly in a real field. These are the different references we can use in our research work. Total 31 references I use. Thank you so much. I am happy to answer your questions now. Thank you. Hello.
Thank you for your presentation. I
Thank
think
you. Thank you.
no questions right now. Next, we have Neha Kalia presenting the paper titled A Secure and Resilient Fog Computing Model for Real-World Fog IoT Application.
Am I audible?
Yes,
Hello,
Neha, you are audible.
am I audible? Okay.
Yes, yes.
Okay, is the screen visible?
Yes, your screen is visible.
Thank you. So, very good afternoon to all the esteemed speakers and guests here. Today, I am here to give a presentation on topic a secure and resilient fog computing model for real-world fog IoT applications. The paper ID is 1614, and we are three authors here: Dr. Digambar Pawar, me, myself, Neha Kalia, and Golak Bihari Dal. So as we know that as the number of IoT devices increases, the latency and bandwidth challenges also increases. Earlier, only we had two layers. One was IoT devices, that is known as edge devices, and the second one was cloud. So the cloud only processing cannot meet all real-time requirements. To solve this problem, fog computing was placed in between IoT and cloud. But the cloud was not having any resource constraint, and fog devices are actually resource constrained devices. So security becomes a major concern because fog is distributed in nature, as well as we cannot apply all the security measures which are applied on cloud on the fog computing. So, when we are building any model with three layers, IoT, fog, and cloud, we need to balance security and performance. At the same time, due to security, we need to provide anonymity, mobility, authentication, and resilience. Resilience here means a system's ability to anticipate, absorb, and recover rapidly from failures or disruptions. By disruptions, I mean to say, for example, node malfunctioning, lost network, etc. So, to solve these problems, we need to develop a generic architecture, model it mathematically, and simulate it on real world. So, we had done reviews on existing fog security. So the work which is there in the literature discuss about privacy, authentication, resource management. But what happens is every work here is working on different architectures. So the protocol is right. It is actually providing authentication, anonymity, privacy, depending on the need, but they work on their own models. So our main aim here was to develop a generic fog IoT architecture with some security embedded in it, and that can be used to design further protocols to provide authentication, privacy, anonymity, lightweight, etc. So here the proposed infrastructure also has three layers: cloud, fog, and IoT. Here we have one administrator administering system which we called as cloud, or for most of the protocols registration authority sits here, and we have fog nodes which executes latency sensitive tasks. So as you can see here, this is the model. At the lower end, we have patrons in one implied assemblance. Implied assemblance we termed as a fog area. Geographically distributed IoT devices. Then we have convergence point from where IoT device will communicate to the fog nodes, and then we have cloud and fog communication. This model will be discussed as per the slide goes. So in our architecture, the first thing is administering subsystem. It is the backbone of the proposed architecture. So what happens here is whatever security related parameters which are being distributed to either fog device or IoT device will be definitely transferred by administering subsystem only, and it will be taken care of all the session keys and any anonymous ID also. Second comes a convergence point. As you can see here, second convergence point. So convergence points are a device or a set of device which are there presented in the fog layer. Now these are resource constrained devices, but still they are well capable to provide some services to the IoT devices. So it is expressed as delta, and we have some vector of elements here. One is its alphanumeric ID, which will be assigned to each convergence point. Then we have its physical public and private key. Then we have its location. Then the ID, unique identification number of the implied assemblance here. As you can see, the third step, implied assemblance to which it will provide its services. And then hardware and software specifications. Next, we have patrons. A patron indicates a client. It is a device which can do basic computation, like it can do hashing. It is able to generate a random number, its own ID, and it can concatenate, etc. Some works it can do. A patron also have a unique alphanumeric string which is associated to it, given by definitely administering subsystem. So what happens is whenever a patron is registered, it will place its request to convergence point, and convergence point will forward it to cloud. Same way, it also has public and private keys, its location, and a unique identifier which indicates it is in which implied assemblance. Third last one is implied assemblance. So it is a region. I can say it as a geographical area also, where the patrons are present. So actually there is no physical boundary. They are logically logically collected to a single space. So here we have, for every implied assemblance, we have a unique alphanumeric ID. We have the number of convergence points which are connected to a single implied assemblance, as well as a number of patrons which are there present in a single implied assemblance. Now, final comes as a demand. A demand is actually an application or task which will be built by patron and accomplished by a convergence point. If a convergence point is resource constant and cannot work on that specific task, it will be forwarded to the cloud. So, for a demand, there are many security sensitive components will be there. So, whenever a demand is registered, all security sensitive information will be given in the vector of elements. So first will be the ID of the demand. This ID will be a derived attribute and will not be included directly. It will be the job of administrating subsystem to allocate for every demand to allocate a alphanumeric ID. Then it also holds a list which patrons can actually generate the demand and can forward it to the convergence points. Next we have SL. SL is security level, which informs to the system that the submitted task, whether it is sensitive to for security or only performance is the thing which we need. So actually we have three values: k is equal to 0, 1 and 2. If the application needs only performance and security is not required, the value of k will be 0. If moderate security is required, value of k will be 1. Else, if high security, if we need a very high level of protection, value of k will be 2. Then we have mobility assistance, which holds a binary value. If patron needs mobility assessment, it will be 1, else it will be 0. Next, we have NS. NS stands for no segments. It stands that whenever a convergence point alone is not able to complete the task will be divided and individual jobs will be given to the connected convergence points. Next, we have context aware. Context aware means if the service is location aware, it will be set to 1, else 0. Next, we have if any job needs to get a quick response, say for priority, higher priority, the quick response will be set to 1. Next, we have RR. RR is resource required, which is the most significant component of demand. Here we need to check that whether our demand is CPU bound or storage bound. See, if it is CPU bound, means it is taking more time of CPU, K is set to 1. If it is the result is giving us more parameters to store, the storage bound, then L will be set to 1. So this was all.
Sorry to interrupt you. This is just a gentle reminder that 1 minute is left for your presentation.
Okay. So here is the network setup phase where we can see a convergence point gives all the required parameters to the administering subsystem. The convergence point captures details of patrons, its features, the implied assemblance in which it will work, and the cloud server to which it will be connected. So administering subsystem process the request and it will grant all the required details to convergence point as well as to the neighboring convergence points also. Now, when we come up to the demand, a patron will generate a demand. This demand point 1 will be sent as it is as a packet to the administering subsystem. ACE will allot one demand ID and will forward it to all the nearby convergence point, and then the specific demand will be responded. So here we have task submission. Task is executed at the allocated convergence point. So now once request is placed, patron receives unique ID of the demand. The patron can submit the task to the CP and can get the requested services. We also have an assisted head of thing where if a patron is mobile in nature, if the mobility triggers, then we need to do the handoff. So suppose a patron agent while moving out from one implied assemblance, it needs to detect and relate to a new convergence point where the identity of the patron will be verified, the identity of the demand will be verified, and then it has to provide the demand ID to the new convergence point. New convergence point will connect to the administering subsystem, and then the task will get completed. In the same way, AS is responsible to monitor the state periodically, and a report will be sent periodically from CPs to the AS. We also simulated it on the iFox simulators. We have different configurations depending on the number of administering subsystems, convergence points, and patrons used. We recorded the energy consumption and application delay based on that. And depends on the security. We know that the main reason this architecture is good is the main novelty is, as one patron is connected to multiple CPs, and CPs are anonymous, they don't know to which different CPs a patron is connected. So even if anyone impersonate a patron or impersonate a convergence point, the security will not lose. Yeah, so conclusion is, we have a fog architecture that balance security and performance both. We can ensure anonymity, secure communication, fault tolerance, and load balancing. It also supports mobility and node authentication. The design is modular, as I told, that the task can be, the jobs can be broken and given to different convergence points, and it is applicable to some domains as smart grids, transportation, etc. And the further work is to enhance trust, transparency, and scalability in this domain. These are the references being used, and I'm thank you and grateful for your time and presence. Any queries, I am happy to answer.
Thank you for your presentation, Neha.
Thank you.
Now we have Neeta Namdev Thakaware presenting the paper titled An Explainable Deep Learning Model for Multi-Class CKD Staging and Early Risk Prediction Using Clinical Biomarkers, Survey, Research Gaps, and Proposed System. Neeta, you may start your presentation.
Yes. Am I audible, ma'am?
Yes, you're audible.
Thank you. So, good afternoon, everyone. I am Neeta Takule. Today, I am presenting my research work on an explainable deep learning model for multi-class CKD staging and early risk prediction using clinical biomarkers, survey, research gaps, and proposed system. My paper ID is 1540.
Neeta, please start
So,
your presentation.
yes, as we know, the CKD is one of the major and non-communicable disease affecting millions of people worldwide. It is a progressive condition that gradually reduces kidney functions over time. If it is not detected early, it can lead to several complications like kidney failure, cardiovascular diseases, and also need for dialysis or transplantation. One of the biggest challenge in CAD management is that if not detected in early stage, it is not detected in early stage. As a result, many patients are diagnosed only after significant damage has already occurred. So, according to the clinical guidelines, the CKD is classified into five stages, ranging from mild kidney diseases to severe kidney diseases. And conventional diagnostic approaches often fail to capture the complex relationship between the multiple biomarkers and disease progressions. So, in recent years, many machine learning and deep learning have been widely explored for CKD predictions. However, still there are some limitations exist. So, most Existing studies focuses on binary classifications. That means only it is able to find out whether there is a CKD or non-CKD, where such predictions are insufficient for clinical decision makings and treatments. Some many models lack interpretability and use smaller data sets, which does not support early risk predictions. So this indicates there is a need for a clinically interpretable systems which capable of multi-stage CKD predictions and early risk evaluation. So to address these challenges, my work proposes an explainable deep learning framework for multi-class CKD stage predictions along with early risk assessment. And the objective of here to provide explainable AI integrations, multi-class CKD stage predictions, and early risk predictions assessment. Sorry. So this model is actually divided it is consist of 6 major phases. The first phase comes with data acquisitions, where clinical data set including biomarkers such as serum, creatinine, blood urea, hemoglobin, blood pressure, glucose strains, and EGFRs are collected. Second phase is about the data preprocessing, where missing values are handled and features are normalized using the normalization functions, and also encoding techniques are used to convert the categorical data to the numerical data. Next phase is CKD stage alignments, where this EGFR value, which is called as estimated glomerular filtration rates, where these values are used to classify the patients into 1 to 5 stages. 1 is a mild stage and 5 is the severe stage. Next phase is about the feature selections, where important biomarkers are selected using the correlation analysis and random forest importance. Next phase is deep learning model, where the proposed model combines the dense neural layers with LSTM based temporal layer for CKD predictions, where dense layers are basically captures complex relationship among the features, and LSTM's layers are used to model temporal patterns in the patient data. Next page is about the risk assessment. That is the last page, where patients are categorized into the low, moderate, and highest risk group. The important highlight of this model is the interpretability. To make the prediction transparent and clinically meaningful, we integrate 2 explainable AI technique, that is shape and line, where shape shows the combination of each feature to the predictions, and line we are using or it is explains individual predictions locally. So this method helps clinicians to understand why a particular prediction was made, and helps to increase the trust on the framework. So this is the result that our model is designed to achieve, where our goal is to perform the got the high performance in multi-class classifications and expected to deliver strong accuracy. It provides high interpretation and better generalization compared to the traditional models. And so I can conclude my research addresses the key gaps in existing CKD prediction systems by moving beyond binary classification to stage-wide classification. The proposed model not only predicts CKD stages, but also assess the future works. And for future work, we plan to extend this model using larger and more diverse data sets, and incorporate multimodal data such as medical imaging and electronic health records, and to develop real-time clinical decision support system. Thank you. I'm waiting for the questions.
Thank you for your presentation, Neeta. I believe there are no questions as of now.
Thank you.
So, our next presenter is Yash Divekar, who will be presenting the paper titled EduRag, a confidence-weighted graph rank framework for multi-hop educational question answering.
Hey, am I audible to everyone?
Yeah, you're audible.
Yep. So, hello everyone. I'm Yash Deveka. I'm a student from YSMS IIT, a finance student, and I'm here to present my paper behalf of my team, which is basically EduRag. I believe the paper is visible. Uh, good evening, everyone. I'm glad to present this paper at this conference, and I'm happy to listen to all the fellow publishers, and I'm thanking you to attend this meeting, and I'm thanking you to listening to me. So here I have a paper. The paper ID is 1653, EduRag, a confidence-weighted graph rag framework for multi-hop educational question answers. So the first point is any question related to a education background or somewhere else is a formulation of multiple parts, like for example, which we have over here is how is a vanishing gradient problem related to LSTM gating. Over here we can have multiple concepts in the same statement, and the graph needs to retrieve the information from multiple points and create a chain. Like over here we have back propagation, gradient dynamics, and gated recurring, and even some parts of vanishing gradients and LSTM to be considered into this answers. The current graph rag frameworks actually lack this problem where they cannot create a proper chain of thoughts from one part to one node to another node and create a semantic understanding of what the answer should be. This is where the graph lag helps us. Graph lag has multiple components, which helps us into first of all noise extraction by considering weights to the triplets by breaking a reasoning chain. So as we consider over here, we have a proper reasoning chain where from one node to another node, why it should be traversing through it. It has an opaque retrieval and a domain mismatch. Like it has an understanding of what kind of a domain we are working in. A better understanding of the proposal of edurag which we are presenting is the confidence which is used as a filter while creating the triplets and considering them as nodes and the edges of the graph should not just be a filter to be said like should this be added to the graph. Rather it should be the structure of the entire rag pipeline and should help the rag improve the confidence and improve the accuracy while also having better citations and better understanding of why this answer has been built. The entire pipeline is actually has four different stages where four different new concepts which are novel to us have been presented over here. This is a simple representation where we will move deeper into the C1, which is confidence score extraction, C2, confidence weighted Leiden community detection, the C3, which is LLM guided adaptive traversal, and C4, which is parallel multi-seed convergence. We'll move into the detailings of these concepts in the further slides. For now, we have this entire pipeline which we will be following in this, where a document is ingested, chunked, and triplets are extracted with a confidence score, where the first algorithm of C1 is implemented. Then a graph is built, and some communities are detected in C2, and it is saved into a ChromaDB. When next time a new query is initiated, a seed entity will be selected from this graph, and then an LLM traversal will happen, which will follow both the strategies, and an answer is generated. In this way, we are increasing the accuracy and the citations of the answers with better reasoning. So, we discussed about C1, C2, C3, and C4. What exactly is that? C1 we propose is confidence score extraction. Basically, while creating triplets, instead of considering just the triplets into the graph lag, we will also consider these specific scores like factuality, specificity, and coherence to be computed for each triplet, giving more context and more metrics to the pair, and having more metadata to be filtered and processed onto. Using these scores, we will be considering them into the graph itself. Instead of just considering them to filter out which should be part of a graph and which should not, we'll move this course towards a community detection algorithm where we will use these as a weights to the Leiden detection algorithm. Over here, the problem is in a basic standard Leiden, every single node is as same as the previous node. and the relationship has the same importance. There is a possibility that in a corpus, two of the nodes are related to each other with more accuracy and more confidence than another two. But because we are not considering these metrics in the further computations, Leiden will not provide accurate communities. Here, if we add the confidences and the matrix which were computed in the previous slide, in the previous step, we can improve the community detection and improve the accuracies of the answers. In this way, the more accurate and the more related nodes are considered a part of a community rather than considering everyone as a part of a community. Here, if we can see a simple representation, is the thickness represents the computations and is a confidence showing that these two nodes are more related to the other two pair. Now we have a graph created with communities detected into it. Here comes the next part, that is the single hop and or multi hop traversal. In standard rack systems, standard graph rack systems, we have a problem of k hops being a static part. Every single graph rack has a part where there will be a source node and there will be k hops from that node which will be retrieved to create the context and passed to the LLM. But does I believe that we don't get a proper accurate traversal of graph using that strategy. There is a high chance that the graph traverses or the neighboring nodes are not actually related or required for the answers and are just a noise in the context of which is passed to the LLM. Here we provide L3, which is LLM guided adaptive traversal, basically creating a graph as the source of truth and letting an LLM use these tools, which is get neighbors, get path, get community, get subgraph, and get community members, and multiple more, to be acted and used to traverse this graph in a semantic order. Every single time, the LLM will basically figure out, okay, this is the starting point, here are the neighboring nodes, which node should I traverse? Every single time it decides should I traverse this node or not, and it takes those steps. In this process, perishing the nodes which are not required or not expected to be providing more context to the required answer. Then for the next selected nodes, it will again traverse and decide should I traverse the next neighboring nodes. In this way, letting the LLM traverse the graph in a semantic fashion and understanding where should the traversal move to get better answers. Here, there's no k, there's no specific limit of how many nodes will be picked or how many depth will be picked. There is a simple LLM deciding should I move forward or should I perish this branch. Because of this, we need to add some limitations. And the limitations which we provide is 30-second steps timed for the LLM to decide, and a 15-step hard cap, which will decide what is the maximum depth LLM should traverse before deciding, okay, let's stop. In this way, the LLM is traversing through the graph in a semantic fashion and moving towards the answers more better. But the bigger problem which we saw at the first was every single question is not a single entity or a single node from where the thing starts. A question, for example, which we had over here at the start, had at least multiple entities. The question itself has an entity called as vanishing gradient and LSTM. So every single question will have one or more entities or one or more nodes or one or more starting points from where the traversal should start. Instead of traversing every single node at one by one or just relying on one traversal path, we will traverse into a multi-seed convergence or a multiple uh, traversal strategy where a C4 relies. Basically, we pitch that we will traverse through all the entities at once in an asynchronous operation and then figure out where the graph should be traversing. Once the
Excuse
two
me,
nodes,
Yash.
yes,
Sorry to interrupt you. This is just a gentle reminder that 1 minute is left for your presentation, so
yep,
please conclude.
sure, thank you. So over here, which we can see that multiple entities will be part of a single question and will be traversed in an asynchronous manner. And the LLM will try to reach to multiple entities and find common paths, and this is where the multiple conversions comes in picture. In this way, we are providing four different implementations of four different novel ideas to be part of a graph rack system. This is the shift which we are pitching, that a basic graph does not strengthen the relationship. It rather just filters out based on the relevance. Rather, we consider that confidence into the uh, traversal algorithm as well. The clustering algorithm improves because of the confidence, and the retrieval strategy of LLM driven traversal improves a better um, traversal towards the graph. In a sense, we will move towards the nodes which will provide us the answer, and we will not move towards the nodes which won't provide us the answer. In a way, reducing the noise and decreasing the unnecessary context which can be added. So, after adding all these structures, what we saw are these scores where our rogue L, bird score were seen. What we did was we added every single part like C1, C2, C3, C4 one by one to see that every single step or every single part idea was increasing our accuracies and performances by margins. And at the end, all the four working together provided amazing results with these 25.6% improved rogue L score and 8.3% improved birth L score. This is what we have provided
Yes,
pitched.
Yash.
Yes.
Sorry to interrupt you. 10 minutes allotted for the presentation are over,
Sure.
so please conclude.
Yeah, that is it. The next part or the future scope of this idea is just to integrate multiple parts, like deciding a better traversal policy and providing a better understanding of cross documents. As what we were doing right now is just a single document graph traversal. Here are some references which we used, and there are some more. There are total 15 references which we use. Here are some top five which we are considering. And thank you. This is what we pitch. I'm open for questions if there are any.
Thank you for your presentation, Yash. I don't think there are any questions.
Thank you so much, everyone. Have a nice day.
Have a nice day. Our next presenter is Ishita Mahalle, who will be presenting the paper titled Mathematical Modeling and Algorithmic Evaluation for Explainable AI.
Yes. Should I share my screen?
Yeah.
Check. Okay. Is the presentation visible?
Yes, that's possible.
Okay. So, good afternoon, everyone, all the judges, professors, fellow researchers, and all the participants. So, I'm Yashita, and on behalf of my team, I'm here to present our research paper, which is Mathematical Modeling and Algorithmic Evaluation for Explainable AI. Before I begin discussing our work, I'd like all of you to imagine a simple situation. Imagine a doctor which is receiving a diagnosis from AI system without any explanation of how that conclusion was reached. The prediction may be completely accurate, but the doctor has absolutely no idea why the AI made that decision. So, would the doctor confidently prescribe treatment based solely on that prediction? Most probably the answer is no. So now think beyond healthcare. The same issue exists in banking while approving loans, in legal systems while assisting judicial decisions, and in autonomous vehicles while making driving decisions, and in many other domains where human lives and critical decisions are involved. So today, artificial intelligence has become incredibly accurate, but accuracy is no longer enough. So if we cannot understand the reason behind an AI's decision, it becomes difficult to trust it, validate, or deploy it. So that this is exactly the challenge our research addresses. Uh, so uh, uh, the artificial intelligence models are often referred to as black box models because they provide predictions without revealing the reasoning behind those predictions. While this may not seem very problematic in other domains such as entertainment applications, so it becomes a serious concern in critical domains such as healthcare, finance, insurance, etc. So the major challenge is not only developing intelligent systems, but also ensuring that these systems are transparent, trustworthy, and explainable. So existing machine learning models are excellent at making predictions, but they fail to provide explanations. So the gaps which we observed in the existing systems are that firstly, the most evaluation methods concentrate primarily on performance metrics such as accuracy, precision, recall, or F1 score. So these metrics tell us how well a model predicts, but they do not tell us whether the explanation generated by the model is meaningful or reliable. And secondly, popular explainability techniques such as SHAP and LIME are widely used to generate explanations. However, there is no universally accepted mathematical framework to evaluate the quality of those generated explanations. So different researchers use different metrics and evaluation protocols, different data sets, and it is difficult to compare one explainability technique with another. So the important limitation is the absence of an integrated framework that will bring together the complete pipeline, like from data selection and model prediction to explanation generation, evaluation, visualization, and final recommendation in one unified workflow. So these observations motivated us to develop a more comprehensive and standardized evaluation framework. So what we are aiming to do here is that our system is capable of generating explanations for machine learning models using both CHAP and LIME. And importantly, instead of relying on traditional evaluation techniques alone, we introduce a mathematical framework that measures the quality of these explanations. Uh, so let's move on to the methodology. Our workflow begins with collecting the data set, followed by preprocessing to clean and prepare the data for training. We load the trained machine learning model and pass it to our explainable AI engine. The XAI engine generates explanations using two explainability techniques, as we know, SHAP and LIME. And generating explanations is only the first step. The most important contribution begins from here. So the generated explanations are passed into our metrics engine. So the metrics engine part is what we have developed ourselves, where we evaluate them using the mathematical framework. And finally, based on these evaluation scores, our system recommends which explanation technique performs better and provides a more uh, more interpretable assessment. So this was all about the workflow. Now this is the workflow for the project which we have made. So I'll not get into the detail of that because we are here, we are discussed to core the core idea. So uh, let's move on with the next one. So we have selected SHAP and LIME. So both aim to explain machine learning prediction, but they work totally differently. So SHAP is based on game theory. It treats every feature in a data set like a player in a team and calculates how each feature contributes to the final prediction. So one of its biggest strengths is that it provides both local explanations, meaning explanations for an individual prediction, and global explanations, showing the overall behavior of the model across the dataset. On the other hand, we have LIME, which is local interpretable model agnostic explanations. So LIME focuses only on a single prediction at a time. So it creates a simpler surrogate model around that specific prediction and identify which features influence the decision the most. So SHAP explains both the overall behavior of the model as well as individual predictions, whereas LIME concentrates only on explaining one prediction at a time. So when we reviewed the existing literature, we found that researchers evaluate explanations using many different metrics. Some evaluate soundness, some other measure stability, some focus on fairness. Although each of these metrics measures an important aspect of explainability. So they all work independently. So imagine evaluating a student's performance based only on their mathematics marks while ignoring all the other subjects. So this evaluation is incomplete, right? So similarly, existing explainability evaluations methods measure only isolated properties. So it is difficult to determine the overall quality of the presentation. So now we are done with understanding the core concept of what we are aiming to do. Now we have combined all these important aspects into one unified evaluation framework. So let's start with that. So our first proposed metric is the structural soundness score. We call it SSS. And like we have what we have done, we have taken similar kind of metrics, combined them together and made three different metrics out of that. And these are behavioral, like we have made this according to the behavior aspect, not the performance aspect. So these are the categories of how they are divided, and this is the first metric. So the idea behind this is actually very intuitive, that suppose an explanation tells us that certain features are extremely important for a prediction, then logically if we remove those important features, the prediction should change significantly. So if removing so-called important features barely changes the prediction, then the explanation was probably misleading. So SSS measures whether the explanation truly identifies the features responsible for the model's decision. So a value close to 1 indicates that the explanation is more faithful and actionable, and a value closer to 0 suggests that the explanation is unreliable because unimportant features appear to influence the prediction more than the important ones. So this was the first matrix. Now, our second contribution is the local stability score,
Excuse me,
LSS.
Ashika.
Yes.
Sorry to interrupt you. This is just a gentle reminder that 1 minute is left for your presentation.
Okay, sure. I'll concluding in next 2 minutes. So imagine asking the same question twice with only a tiny little change in the input. So small variations in the input should produce almost identical explanations. So LSS measures exactly this behavior, and it checks whether the explanation remains stable even when very small perturbations or noise are added to the input. So, in simple words, LSS tells whether the AI explains itself consistently or not. This is the last one. This is HAS. So, while mathematical correctness is important, AI explanations are created for humans. So, an explanation should not be technically correct but also easy to understand, fair across different groups, and consistent with expert knowledge. Therefore, this metrics combine three important human centered aspects, which are expert consistency, fairness, and understandability. So instead of treating them separately, we combine them using a geometric mean, ensuring that weakness in any one aspect significantly reduces the overall score. So this is the only one metrics in which we have taken the average mean. The other two are developed by us. So this prevents a model from appearing trustworthy simply because it performs well in one dimension while performing poorly in other. And this is the biggest contribution. After proposing the three independent evaluation metrics, we wanted to provide researchers with one simple numerical value which represents the overall quality. So this leads to the development of unified interpretability index. So instead of analyzing multiple scores individually, this combines all the three, which is SSS, LSS, and HAS, into one comprehensive score. So if UII value is close to 1, it indicates that the explanation is simultaneously faithful, stable, and aligned with the human reasoning. And a lower UII immediately indicates that the explanation fails in one or more of these essential dimensions. So this is important because previous research lacked a single standardized metric for comparing explainability methods. So yes. So rather than relying on scattered metrics, we are providing with a standardized approach to evaluate explanations. So to conclude, I will say that for many years, artificial intelligence has been evaluated primarily based on how accurately it predicts. But as AI continues to influence critical decisions affecting human lives, accuracy alone is no longer sufficient. An AI system must also be transparent, it must be trustworthy and understandable, and most importantly, its explanations should themselves be measurable, and that's what we are doing rather than inventing our arbitrary mathematical formulas. We analyzed the limitations of the existing interpretability metrics and derived a new behavior driven evaluation frameworks. So yeah, that's it. I conclude my presentation. Thank you everyone for listening, and I would be happy to answer any questions by the session chair.
Dr. Ahire, do you have any questions?
Sorry, I'm just joined.
Thank you, Ishita, for your presentation.
Okay, thank you so much. Thank you so much.
Now we have Vrinda Bhumkar presenting their paper titled EEG-Driven Jewelry Recommendation System, Analyzing Consumer Preferences with Machine Learning. Before we resume with the presentations, I'd like to introduce our session chair who has just joined. Dr. Lomesh Kautik Aire is an assistant professor in the Department of Information Technology at Vishwakarma Institute of Technology in Pune, India, specializing in machine learning, quantum computing, and generative AI. With over 17 years of combined experience in academia and industry, he actively contributes to teaching, research, and the application of emerging technologies in information technology education. Welcome, sir. Would you please like to share a few words with us?
Yeah, good afternoon to all. I would like to all the best to all the participants today. Due to some meetings, so I joined late, but I will continue with the further presentations. Thank you all. Best of luck.
Thank you, sir. Vrinda, you're not audible. Vrinda, your screen is visible, but you're not audible. Vrinda, are you there in this session? We'll be moving forward with the next presentation. The next presenter is Sonal Vij, who will be presenting their paper titled From Smart Homes to Human-Centric Habitats, a framework for intelligent living environments.
Hello.
Hello, Sonal.
Hi, Sanskriti. Is my screen visible?
Yes, it's visible.
Okay, just a second. Um, is it scrolling?
Yes, it is.
Okay. Hello and good evening, everyone. My name is Sonal Viz, and I'm an architect by profession. I have completed my bachelor's in architecture from Ramya Institute of Technology. This paper, ID 1893, is a joint work with Professor Tarun Kumar, who is an academic at Technological University of Dublin. Our paper asks a simple question. Smart homes have become technically sophisticated, but have they really become smart? We introduce HCAH, human centric adaptive habitat, which keeps the occupant at the center and not the device. Now, let's look at the problem. Sanskriti, is my screen completely visible or is it shaded?
It's completely no, now the right half of it is shaded.
Yeah, sorry, I'm so sorry. Can I
It's
just...
gone. It
Yeah.
just
Okay,
appeared
done. Sorry for the interruption. Yeah. Now let's look at the problem that we are facing. The smart homes was meant to adapt to who we are. Instead, it reduces the domestic life of the occupant to four rigid states. That is when the occupant is at home, when they are going out, when they are sleeping, or when they are waking up, which has real consequences. It treats the occupant just as a source of energy and thermal data. The occupant is unable to control their own data. The system shows serious bias in emotion recognition, and those who need the support the most, women, the elderly, the neurodivergent individuals, joint families, are exactly where the system is failing. So, how did we build this? As shown in our paper as well, we have done an integrative review across 7 steps. 1 and 2 is where we establish the problem and we identify the gaps. 3 and 4 is how we develop the framework and how we apply it spatially. 5 is our comparative analysis with our case studies. 6 is where we showcase our app prototype, and 7 is our validation roadmap, which we should take ahead. Now, before we establish the gaps and we identify the problems, let's discuss the case study. This case study is a 7 BHK penthouse, which literally had everything. It had sensors, automated lighting, climate control, Alexa, but still somehow it failed the residents. Sensors used to flood at night, it used to wreck the sleep of residents. Staircase sensors used to fire out of nowhere. And residents also told that the operating the curtains manually was way faster than giving commands to Alexa because it was unable to recognize their dialect. This case study is not the only one. We have North House, we have Aware Homes, we have Emotion Aware Homes. There is a slice of what they cover, which is required at the moment. You may ask, a slice of what? Let's get into that. So there has to be a core shift from the existing system to HCAH. Today's paradigm puts the device at the center. The device will control the energy efficiency, it will control automation, security, but the occupant can only manage it externally. What HCAH does, it keeps the occupant at the center, and all the intelligence is processed on device. Our premise is reflexive intelligence. So, for instance, when we sneeze, our eyes close automatically. No decision is required for this action. A home should respond in the same effortlessness. A system that learns once is not adaptive, it is automated. HCH helps to learn and update the system as the occupant does. Now let's look at the framework. Our framework is a multi-layered framework. It is not separate but overlapping dimensions of one person. Here I want to share one example, like how we go if we want to get an eye checkup done, we go to the eye doctor. The eye doctor places the metal frame over our eyes. They will keep placing the lenses one after the other so that the final vision is as clear as possible. Now imagine these lenses are different layers. Each one has its own significance, but together, once these layers start to overlap, we get a clear picture of what exactly has to be resolved. Now, let's look at the biological reference of it. For instance, cortisol in human body drives both stress and circadian rhythm. Poor sleep will deepen our emotional fragility, which will affect our focus and which will in turn affect our behavior in society. This just tells how each layer, biological, emotional, behavioral, cultural, neurological, Each layer is interconnected. Now, this framework draws on 4 disciplines. First is environmental psychology, where we study that a view of nature will give us a speedy recovery. Second is neuroarchitecture, which states that ceiling height, light activate a certain region of brain. Third is chronobiology, which says that daylight and sleep will affect our day-to-day well-being of an individual. And fourth is cultural research, which says that the Western nuclear family norms just fail in our Indian household context. So, on the right are all the commercial systems that we usually use in our homes, which is Alexa, Samsung Smart Things, Apple HomeKit. Q's is one of the most used residential automation experiences all over India, but they just fail to sense the biological, emotional, behavioral, cultural, and neuroarchitectural states of an occupant. But at the same time, HCAH does. Now, one of the overlap can be a biological state and an emotional state, which in turn gives where we get a bioadaptive therapeutic habitat. This means the home will adapt to who you are and not what you command. One example is the lighting of the house will shift across a woman's menstrual cycle, energizing in the follicular phase, quieting in the luteal phase. And women who are facing PCOS issues, the circadian aligned lighting can help them relax and recover faster. Now, this framework also maps on a real built fabric. Configuration A, where you see is a 5-story joint family home. Shared spaces are on the ground floor and the fourth floor, whereas private spaces are shown on the first, second, and third floor for each individual member. Configuration B is a compact 2 BHK, which is the most common configuration amongst many Indian households, where the spaces have been divided using is divided over a single floor plate. So these shared spaces like living, dining, kitchen will be all over the house, whereas the private spaces like bedrooms and multifunctional rooms can turn into a study, nursery, or play area as per our requirement. And then there will be semi-private rooms like a puja room or a TV room. So the same framework basically can vary in different houses with very much different space configurations. Now, to show the feasibility of the framework, we have built a working smartphone prototype on Google Stitch. It runs the full loop. First, we have our welcome screen. Then the occupant can select the type of housing. If they are already a part of existing hub, then the occupant can add their personal details, medical history. They can sync their smartwatches, smart rings, and health patches with the app. Each profile of an individual will be password protected and will have a two-factor authentication. As you can see, the last 3 slides are the responses of the app of 3 different occupant needs at 3 different times of the day. Now, what does this contribute? As a society, it promotes an environment with good health, less stress, which targets. Hello?
Yeah, sorry to interrupt you. This is just a gentle reminder that 1 minute is left for your presentation, so please continue.
Sure. Thank you, Sanskriti. Thank you. So I was saying, as a society, it promotes environment of good health, less stress, which targets the key drivers of preventable urban illness. As an industry, it generates and increases the rate of employment. This framework cannot just be done by smart home professionals. We need architects, we need designers, psychologists, researchers, doctors, engineers, etc. to achieve our end goal. And the third and the most important, the ethics of it. No raw data shall be shared on a cloud, and the framework will show equivalent performances across all demographics. I want to be really candid. This framework is theoretical and schematic at this point and anchored by a single case study. Validation is the next step. So, pilot homes monitored over time, cultural studies, multi-generational Indian household studies, and clinical assessment is something which this field is lacking, and the validation through it is required at this moment. To conclude, for most of the human history, intelligence in home was architectural. The orientation of the window, the height of the ceiling, the placement of the bed in a bedroom. As the home became smart, we forgot about this. These five layers that I have described, which it means, what it means is a human being a human inside their home. The gap between what smart home promises and what it delivers is a design philosophy problem, not an engineering one. A home built on these layers treats the person with dignity. The occupant feels known, not just scheduled. It is responded to, not just managed. And the occupant should be support. The home should support the occupant on their difficult days rather than just optimizing on their easy ones. The technology exists, the evidence exists, the professionals exist. What is missing is the design language, and this paper is just an attempt to offer it. Thank you for your time and attention. I'd be really glad to take your questions.
Hello.
Hi, sir.
Yeah. How you are going to achieve data security? As you said that data is not
So
sharing with the
this
cloud.
Yeah. So this is one of the major questions we were also discussing while we were doing this, while we were researching. So basically, the data does not go to it is not stored in the cloud, but it is a in-home device. So basically, like all the data that will be taken from your smart home, that will be just stored in the app. Nothing will be leaking. But if there is a hack, at least the whole cloud is not hacked. Only like one home system is hacked. We are just reducing the size of the hackable system, but we are not completely eliminating it. You are right about it, but at least we are just reducing the size of the hackable system.
But as you described, there is a huge data generating day by day in your smartphone. So how your app can
Okay.
handle it?
So basically, whatever data is stored, so basically the occupant will like it will enter, they will enter their medical history, they will have options to choose if they are anxious, if they get stressed by some situation, they can enter that data, which is password protected, which has a two-factor authentication, which the occupant can control in their hand. At any given point they can retrieve it back. So yeah, that is how right now we are thinking of doing it. But yes, the work is still going on. So as it goes by, yeah, we have to make it more secure and more strong.
Okay, thank you.
Thank you so much.
Thank you, Sonal, for your presentation.
Thank you, Sanskriti.
Now we have Zorzi Duque presenting the paper titled Institutional and Student Digital Twins for the Sustainable Prevention of Dropout in Higher Education.
Hello, good afternoon.
Good afternoon.
Good afternoon, sir.
Okay. I minimize this. Okay. Are you watching the presentation?
Yes, it's visible.
Okay, thank you. This project, or the aim of this project, was to present a digital twin model to verify and test the variables that may lead to students dropping out. It is not easy to define a single model. There are different realities and database with data collected in different ways, which does not facilitate the process of creating a model to understand what leads to students dropping out and also to academic failure. this presentation. Where the problem or contribution. From an isolated alert to an explaining of the table of infrastructure designed to support students. Dropout is not a final event where it results from, for example, cumulative trajectories of performance, integration, economic conditions, and institutional response. Okay, isn't a dropout. It should be observed legitimately and before actual withdrawal. I'm the student of the study. The purpose an institutional and student digital twin model for sustainable dropout prevention. Second, to combine explained, i.e., artificial intelligence, human oversight, proportionate intervention, and institutional learning. Where the central contribution, i.e., or artificial intelligence, does not decide. It flags, explains, and documents information to support professional decision making. Okay, the institution can measure risk, response capacity, outcomes, and continue to prevent. Key message is very important to dropout. Probability is a support sign, not a sentence and not a machine of exclusion. The state of the art and the scientific gap. The first, in the learning analytics, machine learning, SHAE, explaining artificial intelligence, and digital twins converge, but institutional adoption requires governance. The dimension, prevailing evidence, identify gap in model response. First, dropout is the first dimension. Longitudinal and multifactorial phenomenon. And identify gap. Models may individually blame. Model response, integration of the student trajectory with the institutional context. And learning analytics, okay, prevailing evidence, academic, behavioral, and administrative signals. And the identify gap. Alerts do not always translate into support. And model response, closed loop, prediction, explaining, action, outcome, and recalibration. Where the type of the elements I use, for example, use the algorithm machine learning. Okay, the dimension. Where the type of the algorithms? In this project, I use the algorithm supervisor, random forest, SheBoost, and strong ensembles for tabular data. Identify gap, risk of leakage, and suitable thresholds, and poor calibration. Leakage-free pipeline, local validation, calibration, and drive monitoring. Where the SHAE and the dimension, SHAE and digital twins. Okay, providing evidence, shape, local explanation, and dimension representation. Okay, and identify gap, peripheral, explain it, and absent institution. SHAE embedded is the model response. SHAE embedded in human review and the institutional twin with response capacity. Main gap is very important, moving for metric-centered models to responsible, measure, and sustainable socio-technical infrastructure. And where the methodology used in this? I used in this project, we use the design science research. Is a normal use in the information system. Okay, identified for the artifacts combined architecture and analytical pipeline, explanation, intervention, governance, and evaluation. The first element is the problem. Second is define the objectives, the problems, design, the free design, and free elements. The principal elements is to decide to complement your project, and the next step is the demonstration and evaluation to communication the institutional validation. Okay, where the evidence layers used in this project used the the largest number of students included in the study came from the University of the Valencia in Spain, and the other in Portugal. However, some two public institutions, one in Portugal, other in Spain, were used in the study to ensure the model's consistency. Okay, it's very important for these elements. Okay, I'm sorry. No, see this project. I'm sorry. Okay, I continue. And the next artifact, where the artifact development dual architecture. In digital twin links the student state, the institutional response is the capacity. Okay, the element calibrated probability is the formal. Okay, is the oriental explain and human review. Element student twin. Okay, is very important to define the credits, course units, grades, attendance, LEMS, tutoring. Okay, and the institutional twin is very important to define the capacity, service, calendar, critical units. In the governance, it's very important to propose, accept, audit, protection. Okay, calibrate analytics and share and continuous simulate. Okay, but the governments use, for example, the learning cycle outcomes drift equitative, but the chain and critical simulation support action and the calibration and analyze human review. Is the final decision are always contextualized, document and supervised by institutional professionals. Okay, where's the operational development from the risk to intervention? Okay, the artifact is only useful if it turns a probability into proportionality recorded and assembled action. Okay, is 6 elements fundamental. The proposed dropout horizon hours. A second, update states data available before prediction. 3, estimate the risk, validate model, calibrate thresholds. 4, explain factors, global and local drivers. 5, intervene in communication, tutoring, and social support. 6, learn and come credit continuous recalibration. Okay, and the next step is the implementation alternative by digital maturity. Okay, minimum dashboard, transparent rules, more manual review. B, second, student twin, predictive model, more chain and more risk bands. C, integrated twin individual risks, more institutional capacity, and federated benchmarking, multi-institutional collaboration. Okay, and the responsive implementation roadmap. Diagnostics, data, readiness, pilot, who is the step by step, okay, you manage workflow, control using, and the scale, okay? Results, the predictive performance is very important to analyze. Is I use in the two universities, the result in Portugal and Spain, okay, where the interpretation, the evaluation confirms strong performance while reinforcing the need for local validation and institutional adaptation. Okay, it's very important. Interpretation of a result, the random forest, and the stacking of UC benchmark, and is the metrics. The result for the metrics use this algorithmics, random forest, and in the authors. A technical conclusion: the architecture is transferable. Parameters, thresholds, and explanations must be local validation. Okay. Discussion. Okay, is the important variables. Okay, the quality model should assess it. Okay, for example, the quality of the model should assess by its ability to generate effective support and only by metrics is very important to concept. course, for example, course units passed second semester, course units passed first semester, when they contribute for the
Excuse me, Mr.
decision,
Du.
for the test. Attendance, LMS, initial
Excuse me,
performance
Mr.
is
Du.
variable, não é?
Sorry to interrupt
Prioritizing.
you.
Yes. Okay.
You have 1 minute left for your presentation.
Okay,
So please go.
I finish. Excellent factors in the student win. Okay, where the responsibility? Quality alert, quality explanation, quality action, and quality outcome. Okay, and conclusion. Digital twin is a responsible supporting infrastructure is not anime. First, early identification. Represent trajectories before dropout becomes irreversible. Second, actionable explanation. Transform risk drivers into academic, social, and administrative action. Three, proportionate intervention. Ensure we may review careful communication and support suite to need. Four, institutional learning. Connect alert action outcome audit equity type and continued improvement. Main contribution, an apply model that moves institution from isolated alerts towards responsible measure and sustainable student support. Next steps, longitudinal pilots, cohort comparison, subgroup auditing, user training, and federate validation. Thank you for attention. Your question, please.
Dr. Hare, do you have any questions? I believe there are no questions, so we'll be moving forward with the next presentation.
Thank you.
Thank you for your presentation. Okay.
Thank you.
The next presenter is Rashmi R. Chauhan, who representing their paper titled Transformer-Based Hindi SRL Using Dependency Relations. Rashmi, you may start your presentation.
Yeah, sure. Is my screen visible?
Yes, it's visible.
Am I audible?
Yes.
Okay, thank you so much. Good evening, everyone. I am Rashmi Chauhan, and with the guidance of my supervisor, Dr. Charmi Patel ma'am, today I am going to present my paper title is Transformer-Based Hindi SRL Using Dependency Relation. These are the outline of my paper, which I'm going to discuss today. Let us start with the very first thing, that is what is semantic role labeling. So what it is a natural language processing task that decides or that determines the argument related to the predicate or the verb. Let us see example first. Mr. Kalpesh sold computer to Mr. Shriyan. So here predicate is sold. So we need to identify argument regarding the predicate. So argument 1, that is an agent who is the doer, that is argument 0. Argument 1 is the thing which we have transferred or we have given to the other person. So that is argument 1. And argument 2, that is recipient of the object. So this is the core task for the NLP application that can be used anywhere in the applications like question answering system, machine translation, information extraction, and many more. As my title is on Hindi language, so let us take an Hindi example also. Neha ne Mita ko kitab di. Here the verb is the di, and argument which are related to the verb di is Neha ne, that is argument 0, doer. Mita ko, she is the receiver, so that is argument 2, and the kitab, that is argument 1. So finally, we need to obtain arguments of the predicate. Our proposed framework is we have formulated the SRL that works as a token level classification. Here we are using transformer based encoder. Due to very limited data availability of SRL limited data availability, we need to use Hindi dependency tree bank for modeling our for training our model over here. this is our framework. We are starting with the Hindi dependency tree bank data set. This tree bank data is given to the for the pre-processing, and after pre-processing, we are converting the dependency labels to the SRL labels, and finally we are converting the biotech conversion labels from it. This data set is now ready for our SRL model. Now, this data set we can give to our model, that is Mural. We are using Hugging Faces model Mural, transformer based encoder. Now we will train our encoder using this data set. And finally, we will give raw Hindi sentences. We will tokenize it, and the model which we have trained will infer the SRL tags. The data set which is more appropriate for our work is Hindi Preposition Bank. But we can use Hindi Dependency Tree Bank also and Hindi FrameNet also. But the most appropriate data set, that is Hindi Preposition Bank. Right now we are using, as Hindi Preposition Bank is not available freely, we have to use, for training our model, we have used Hindi Dependency Tree Bank as primary data set, and we are working with roughly 14,000 sentences to train our model. Let us take an example. Hindi Dependency Tree Bank. This is an example of data set which we have in Hindi Dependency Tree Bank, and on the right hand side we have Hindi Prop Bank. This is the data which we have in Hindi Prop Bank. Hindi Prop Bank is the most appropriate data set, as we have already argument 0, argument 1, argument. There are several arguments labeled in this data set. But in Dependency Tree Bank, we don't have these labels available to train our model. So what we are going to do is, according to the D relation, that is K1, K2, we are mapping these K1, K2 against the argument like ARG0 and ARG1. So basically we don't have, or we have accuracy of Hindi Prop Bank dataset. We are using Hindi Dependency Tree Bank to train our model. These are the labels finally which we want to give to our raw Hindi sentences. Roughly 24 to 25 labels are there, and these are the Prop Bank labels. This is the mapping of Hindi Dependency Tree Bank label to the Prop Bank label. Suppose I have in D1, in D relation over here in this example, if I have value K1, then that value K1 can be mapped to argument 0. If I have value K2, then that can be mapped to argument 1. So some of the labels, these are mapping of Hindi Dependency Tree Bank to Hindi Prop Bank text set. Here our proposed model is considered as a token level classification model, and it is pre-trained model on 17 Indian languages. But what we are going to do is we are going to derive SRL labels from the dependency labels. Our model is using the batch size of 4, and it will be optimizing our model for 2 epochs with the learning rate of 3 into 10 raised to minus 5. Our model, this is the accuracy which our model is giving. As this was the very first work using Hindi Dependency Tree Bank, there was no baseline model for me for the comparison. That's why with the same data set, I create an SVM baseline model, because previous studies had shown their work with the SVM model. So I have created a baseline model, and my model, right now my model is Mural, that is multi-representation Indian language, that represents more precision, more recall, and F1 score higher than the SPM model. Now, suppose if we give the raw sentence to this trained model, like Chhatra ne sawal ka uttar diya, so my arguments are mostly right. Argument 0, Chhatra is argument 0, ne is also argument 0, sawal argument 1, ka, that is ARG2 attire, uttar, that is true, diya, that is predicate. But here in these two sentences, the ka and ko, that is given wrong argument label. Let us see why. See, according to the above results, ka in Chhatra sawal ka uttar diya is predicted as ARG2 ATR. But our model should concentrate, as it is local level prediction, it should be argument 1. Similarly, with the another sentence, Deha ne Nita ko kitab di, here ko should be argument 2 instead of ARGM exit. Okay, while this approach is computationally good, but But what we understood it is limited to the predefined rules. We are giving some predefined rules to this model, and it is lacking deep knowledge of contextual understanding. So according to the experiment and observation, we have seen that for simple sentences it works well, but when it comes to the long distance sentences like adhyapak ne कहा कि छात्र ने साहब को बुलाया, and if we have some ambiguous post positions like we have say two times, and both the say represents, one of the say represents किसान ने ट्रैक्टर से खेत जोता, तो खेत is place where किसान गांव से शहर आया, तो शहर is the source. Say post position is used in two sentences, and both the sentences have different meanings. So if we are going with the rule based system, it may get wrong predictions on the raw Hindi sentence. Another observations that we made from the previous studies, that we can directly map several of the dependency labels like K1 directly to the argument 0, K2 directly to the argument 1, but there are several dependency labels which are semantically ambiguous. Let us take an example of K3. K3, Hanji.
Sorry to interrupt you. This
Okay,
is
okay.
just a gentle reminder that 1
I
minute
do
is
that.
there for your presentation.
Thank you. K3 is associated with say, so it should be mapped with ARGM, MNS. When it is associated with co, then it should be mapped to ARG2. When it is associated with ka, ki, and k, then it should be marked with ARGM1. So with the previous studies, we have seen that it works well for the simple sentence, but when it comes to the long range dependency, when it comes to the context of a grammatical representation, it might get ambiguous predictions. So we can implement context aware grammatical representation, semantics, supersense annotations, and long range dependency model to improve this issue. Finally, I want to conclude that as Hindi is a low resource language, we have a scarcity of annotated data. That's why in this model, we are converting dependency labels into the SRL labels, and finally we are getting our accuracy. The approach is good, but it has some drawbacks. That drawbacks can be sorted out with the context aware system or data driven model approaches. Future work, we would like to develop the robust and more scalable SRL and however these challenges can be sorted out with the more advanced context aware and data driven SRL model, the references which I have used. Thank you. Any questions?
Dr. Hede, do you have any questions? I believe there are no questions. Thank you, Rashmi, for your presentation.
Thank you, ma'am.
At last, we have Vrinda Bhunkar presenting the paper titled EEG-Driven Rule Recommendation System, Analyzing Consumer Preferences with Machine Learning. Is the screen visible? Vrinda Bhunkar, are you present in this session?
Yes. I'm audible, ma'am.
Yes, you're audible, but your voice is echoing. Vrinda, are you present?
Hello, ma'am.
You are audible, but your voice is echoing.
No.
Yeah, even now.
Now, ma'am, I'm audible.
Yes, you're audible.
Okay. Good afternoon, everyone. Myself, Ms. Vrunda Sushan Monkar from Department of Computer Engineering, Dr. Babasaheb Ambedkar Technological University, Lonere. Today, I am going to present our research paper titled EG-driven jewelry recommendation system, analyzing consumer preferences with machine learning. Okay, ma'am, please go to the next slide. This is the outline of my presentation, that introduction, problem statement, research objective, and so on. Please go through the next slide. Okay. Nowadays, online jewelry shopping provides thousands of design options. Customers usually select jewelry based on appearance and emotions, but most existing recommendation systems use purchase history, browsing history, and customer ratings. However, these methods cannot understand the customer's subconscious feelings. To overcome this limitation, our work uses electroencephalography, which is also called as EEG, which records brain signals and helps understand the user's emotional response while weaving the jewelry. Please go through the next slide. Okay. Current recommendation system have several limitations. They mainly depends on explicit user feedbacks such as ratings and reviews. But sometimes users cannot clearly express their preferences. This system also ignores subconscious emotions during the decision making. Therefore, there is a need for the recommendation system that can understand both conscious and subconscious preferences. So, next slide. The main objective of this research are first to record EEG signals while participants observe jewelry images, then to analyze different brainwave activities, then to combine that EEG features with manual responses, and then to train our machine learning model for preference prediction and to generate the personalized jewelry recommendations. So, in the next slide, there is a proposed framework. This figure shows the overall architecture of our proposed system. First, participants view jewelry images while wearing the EEG device. At the same time, manual responses are collected through a Google form. The EEG signals are then pre-processed to remove noise and extract useful features. These features are used to train machine learning model. And finally, the trained model predict user preferences and recommends suitable jewelry designs. In the next slide, for our in this our experiment, we collected both manual responses by using Google Form and the EEG data by using EEG device. There are a total 45 participants participated in our study. We selected 18 jewelry images from three jewelry brands, PNG, Malabar, and Tanish. Each image was displayed for 10 seconds. Then participant gave manual response as a yes, no, and maybe, while the EEG device simultaneously recorded their brain activity. In the next slide, after that collecting data, pre-processing was performed. First, EEG signal was acquired, the noise was removed, and the data was clean. Important EEG features were extracted. This process feature were then used for machine learning model training and evaluation to the predict user preferences. In our next slide, analysis of brainwave means this table shows how different brainwave changes when users like or dislike jewelry. When participants like a jewelry design, beta and gamma waves generally increase. Indicates the attention and engagement of the user. Theta wave also increase due to emotional processing. Then in the other hand, they when participant dislike any image, then alpha activities increase, showing lower engagement. These brainwave changes help us understand user preferences. In my next slide, the extracted EEG features were used to train and compare for supervised machine learning models. We selected logistic regression as a baseline classifier. Random forest was used because it handles complex EEG patterns effectively. Then support vector machine performs well with high dimensional EEG data. And K nearest neighbor or KNN predicts preferences based means it similarity between EEG feature patterns. So finally, we compared the performance of all four models to identify the best classifier. So this table presents the classification accuracy of all these four models. In between that, among all these models, KNN achieved the highest accuracy of 99.79%. Therefore, KNN was selected as the best model for four recommendation systems. uh, for our recommendation systems. So there are key findings. Our analysis show that beta and theta brainwave contributed the most to preference prediction. Alpha and delta waves had less influence, and maybe class has more difficult to classify because few samples were collected. So overall, EEG signals can effectively support personalized recommendation systems. In my next slide, recommendation process. This slide explains how recommendation are generated. First, the user views jewelry images. The EEG device records brain activity. The signals are pre-processed and important feature are extracted. The trained KNN classifier predicts whether the user likes, dislike, or is uncertain about the jewelry. Finally, jewelry designs predicted as a yes are recommended to the user. So in my next slide, this research introduces an EEG assisted jewelry recommendation framework. It combines neuroscience with machine learning for personalized recommendation. This approach can improve customers' experience in online shopping. In future, this work can be extended using deep learning, larger dataset, wearable EEG devices, and recommendation system for fashion, cosmetics, or other retail products. So, lastly, conclusion. In conclusion, this research demonstrates that EEG signals can capture customers' preferences more effectively than traditional recommendation method. By combining EEG analysis with machine learning, our system provides more personalized jewelry recommendations. Among all these models, KNN achieved the best performance with the accuracy of 99.79%. So, thank you for your attention, or thank you for your listening to my presentation. And I will refer these references. Any question?
Dr. Hire, do you have any questions? I believe there are no questions, Vrinda. Thank you for your presentation.
Okay, thank you so much, everyone.
And with that, we've come to the end of technical session 12E. I'd like to thank all the authors for the excellent presentations and valuable research contributions. I'd also like to thank all the participants for being a part of this session of the 11th International Conference on Information and Communications Technology for Sustainable Development, that is ICT4SD 2026. I hope you found today's session informative and enriching. On behalf of the entire organizing committee, we extend a heartfelt gratitude for your continued support, not only for the 11th edition of ICT4SD, but also for the previous editions. We look forward to welcoming you again at the 12th ICT4SD conference in 2027. All presenters will receive their digital certificates via email within 2 working days. The conference proceedings are expected to be published within 7 to 8 months. We kindly request your continued cooperation with the organizing team throughout the publication process. I'd also like to express my gratitude to Dr. Lomesh Ahire for effectively chairing this session. As a token of our appreciation, we present this to you, sir. Sir, would you please like to share any closing remarks? I think Dr. Idea has gotten disconnected due to some technical difficulties. Now, before we end this session, I'd like to request everyone to turn on their cameras so that we can have a quick snapshot of this session. Thank you everyone for joining today. I hope you have a great day.